First fact, the Big Bang is not the bang of a bomb in an empty dark world, but the moment when space and time themselves began to stretch like rubber without an edge or a center. What we call the creation of the universe in modern cosmology is the start of the expansion and cooling of a hot, incredibly dense plasma from which atoms, stars, and we ourselves later emerged. Importantly, it's not about an explosion in an already existing space, but about the expansion of space itself. Therefore, the question, where is it expanding to, is incorrect. Into nothingness, it's simply getting bigger in itself. Rewinding the film with the equations of general relativity, we arrive at tiny times of the order of 10 to the negative 43 seconds after the beginning, the Planck epoch, where the laws we know lose their power and quantum gravity is required. No fire point do our observations show, only that density and temperature grew insanely, up to 1032 K by estimates. The cosmic microwave background, a uniform echo with a temperature of about 2.725 K, captured the moment light first broke free, about 380,000 years after the start. Its faint splotches, only 10 thousandths apart, show that the infant universe was almost perfect in uniformity and flatness. However, singularity in the school sense is not an established fact, but merely an indicator that our formulas reach their limit of applicability. In other words, creation is not a single frame with a blinding flash, but a long scene where time, space, and energy come into play simultaneously, setting the rhythm for everything that follows. Second fact. To explain why the universe is so uniform on vast scales and yet geometrically almost flat, physicists introduced the idea of inflation, a superfast exponential expansion in the first moments after its beginning. Imagine a small ball that, in about 10 to the minus 35 seconds, increases by tens of e-folds, roughly 60 or more scale doublings. Any wrinkles smooth out, curvature tends to zero, and distant edges, which didn't have time to exchange light, suddenly become identical because they were once neighbors. The key prediction of inflation is the tiny quantum fluctuations of the field, inflated to cosmic sizes. These are precisely what become the seeds of future galaxies. We see their imprint in the microwave background, an almost scale-invariant pattern of spots, but not quite, and a nearly Gaussian distribution, which is what is observed. Inflation also solves the monopole problem, hypothetical heavy particles that would become extremely rare during rapid expansion. But it's important to remember, inflation is a working hypothesis, not a settled truth. There are competing scenarios for the early universe, bounces, ekpyrotic models. The search for the B-mode polarization of the background expected from inflation's gravitational waves has not yet yielded a firm signal. A much-hyped spike was once explained as dust in our galaxy. That is, the theory has beautiful agreements with the data, but its mechanism, which field, which potential, why it started and stopped, remains a subject of hunt. And this is what makes it particularly captivating. In the very idea of creation lies the trace of quantum randomness, stretched to the size of the sky. Fact 3. The seconds and minutes after the start are a separate drama, where the universe acts as a giant kitchen, and the recipe is called primordial nucleosynthesis. When the universe's age was a fraction of a second, the temperature measured in billions of Kelvin, and neutrinos almost instantly detached from the plasma and went into free flight. Around the first second, cooling performs a key trick. The neutron-to-proton ratio freezes at about 1 to 6 because the weak interaction is no longer fast enough to flip them, and neutrons begin to decay with a characteristic lifetime of around 880 seconds. A little more, and at the 3-minute mark, when the temperature drops to about 1 billion K, the deuterium bottleneck disappears. Hydrogen nuclei can finally grab onto each other without being broken apart by inverse photons. After that, everything happens rapidly. The lion's share of available neutrons goes into stable helium-4, while in microscopic fractions, helium-3, deuterium, and traces of lithium-7 are born. The output of the dish is surprisingly precise. By mass, it results in about a quarter helium and the vast majority of hydrogen, what we see in old stars and gas nebulae. This chemical fingerprint works as both a thermometer and a scale. It's sensitive to the number of light particles, effective number of neutrinos, and how many baryons per photon were in the early plasma. Amazingly, these quantities extracted from the minute-long kitchen match what microwave's background observations hundreds of thousands of years after the start provide. There is also a snag, the so-called lithium problem. Calculations predict more lithium-7 than we see in the oldest metal-poor stars. It's debated whether stellar envelope astrophysics or a flaw in our early physics is to blame. But the fact remains, from a scorching, almost homogeneous sea, the universe cooked up a menu in a few minutes from which it would later build all molecules and worlds. The fourth fact is that the creation of the universe was not just the birth of light and atoms, but also the assembly of an invisible framework onto which galaxies are later hung. Dark matter is not a metaphor, but a gravitational necessity. The rotation speeds of stars and disks, the shapes of gravitational lenses, the pattern of acoustic peaks in the cosmic background, and the behavior of merging clusters, like the famous bullet cluster, all point to a large proportion of matter that barely interacts with light and itself, but pulls everything magnificently with gravity. By mass, if considering only matter, it is about 85%. Without this gravitational reserve, the early universe would not have had time to assemble structures by the observable epochs. An important detail: before the formation of neutral atoms, baryons were screwed to photons and trembled with them like a string. Dark matter, on the other hand, did not fear oscillations and managed to draw in advance a map of potential wells, future galactic nests. When, about 380,000 years later, gas separated from light, it began to flow into these wells, and soon, on cosmic timescales, for hundreds of millions of years, the first stars flashed, piercing the darkness and gradually reionizing the intergalactic medium. We don't know exactly what darkness is: hypothetical WIMP particles, axions, or something else. Direct searches are still silent, but the cosmic pattern stubbornly points to a cold character. Otherwise, small structures would have been erased like tracks in wet sand. This is the paradox of creation. Everything visible was born on an invisible framework, and it was precisely the void, that which gives no light, that shaped the places where light would later shine. Fifth fact: the cosmic microwave background isn't just the noise from an old TV, but a baby picture of the universe, taken when it was about 380,000 years old and hot plasma first allowed light to go free-floating. Its temperature today is about 2.725 K, and it's an almost perfect blackbody spectrum, smooth as a taut string. But on this smoothness are tiny wrinkles, anisotropies of the order of 10,000%, just tens of microkelvins. These splotches are a record of sound waves that ran through the early plasma at about c/√3 speed. Gravity tried to compress, photon pressure to expand, and as a result, the rhythm of acoustic peaks was imprinted on the sky. By their heights and positions, cosmologists count baryons, dark matter, and space curvature, yielding an almost flat geometry and a precisely tuned content. The background's polarization adds subtle touches. E-modes confirm the acoustics pattern. A weak gravitational lens blurs the picture and reveals cluster mass. And a curious dipolar anisotropy speaks of our motion through the cosmic gas at hundreds of kilometers per second. The background itself serves as a spotlight for large-scale structure. Galaxy clusters leave their imprints on it via the Sunyaev-Zeldovich effect. And the large but not infinite horizon of that time explains why opposite sky ends are so alike. They were once connected before inflation pulled them further than visible. Even the distance scale, baryonic acoustic oscillations, has survived in galaxy distribution as a faint preference to meet around 500 million light-years away. This is already a ruler by which cosmic expansion is measured in later epochs. Altogether, it's like clues at the scene of an ancient event. The spectrum, the spots, the polarization, the lensing, and each points to the same origin, turning the faint glow into the most accurate chronicle of the early cosmos. The sixth fact. Most astonishingly, the universe's expansion isn't just continuing, it's accelerating, as if someone quietly stepped on the gas of an invisible engine. This conclusion arose from observations of distant Type I supernovae in the late 1990s. The standard candles turned out dimmer than expected, implying greater distances than with decelerating expansion. To reconcile the picture, the cosmological constant lambda is returned to Einstein's equations: vacuum energy, uniformly spread through space with negative pressure. Current estimates suggest it accounts for the lion's share of the energy balance, around 2/3, while dark matter and ordinary matter divide the rest. This dark energy has an equation of state with a parameter W close to -1. This is how it makes geometry inflate ever faster. Yet behind the apparent simplicity lies a profound mystery. Quantum calculations of vacuum energy yield monstrous figures, tens of orders of magnitude greater than the observed value, the most glaring failure between theory and reality in fundamental physics constants. Alternatives exist: dynamic quintessence, modified gravity, scenarios with a slowly time-varying W, cosmic rulers and clocks, baryonic oscillations, weak lensing, clusters, and those same supernovae measure expansion history, tightening the network of constraints. Against this backdrop, a separate intrigue flared up: the H0 tension. Local measurements of the expansion rate and early universe estimates stubbornly diverge by several kilometers per second per megaparsec. Perhaps this is a crack through which a new particle or a different deadline for dark dynamics will seep into physics. If lambda is a constant, a world with a cosmological horizon awaits us. Distant galaxies will one by one fall beyond the edge of visibility. Stellar fuel will burn out, and the future will become infinitely cold. Paradoxically, it is the void, which we usually ignore, that sets the final tempo for the universe's story. Seventh fact. Why does the universe contain stars and us rather than a uniform nothingness after the mutual annihilation of particles and antiparticles? Observations indicate that matter is only slightly more abundant than antimaterial, about 1 extra baryon for every billion-plus photons, and it is this microscopic imbalance that survived the early heat and seeded the entire visible cosmos. How is this possible? In 1967, Andrei Sakharov formulated 3 conditions for baryogenesis. Processes that violate baryon number conservation are needed. Parity and charge conjugate symmetry asymmetry (CP) violation is required, and a departure from thermodynamic equilibrium is necessary. This is not an abstraction. CP violation has indeed been measured in the decays of K and B mesons, and in the hot early plasma, so-called sphalerons of the electroweak interaction were at work, erasing baryon and lepton numbers in the B plus L combination. However, the standard model alone is insufficient. With the open mass of 125 GeV for the Higgs boson, the transition was not turbulent but smooth, and the CP violation observed in quarks is not enough to produce the required asymmetry. Hence the popular path, leptogenesis. Heavy right-handed neutrinos from the seesaw mechanism decay slightly asymmetrically, producing an excess of leptons, which sphalerons partially convert into baryons. Indirect hints: neutrino oscillations prove that neutrinos have mass. Perhaps they are the key. Alternatives: electroweak baryogenesis in extended Higgs models or exotic phases. Verification is underway through multiple channels: searches for neutrinoless double beta decay, fine cosmology of early epochs, accelerator experiments. There is no answer yet, but one thing is clear: the fate of creation was decided by the subtle, out-of-equilibrium chemistry of the first fractions of a second. The eighth fact, cosmic dawn, the moment when the darkness of the first hundreds of millions of years gave way to the first light sources, was not an instantaneous flash, but a flicker of multiple sources that gradually ionized the intergalactic hydrogen. After recombination, approximately 380,000 years, the universe became transparent, but there were no stars yet. The neutral gas cooled, gathering into mini-halos of about 10 to the 5 to 10 to the 6 solar masses, where H2 molecules allowed the first sufficient cooling for population 3 stars to ignite. Likely massive, tens to hundreds of solar masses, living only a few million years and exploding as powerful supernova. Their ultraviolet light tore electrons from atoms, inflating bubbles of ionized plasma around young clusters and the first quasars. The bubbles grew and merged, and by redshifts of about z equals 6, universe age 1 billion years, almost all intergalactic gas had been reionized. This is evident from the Gunn-Peterson dips in the spectra of distant quasars and the sharp drop in the visibility of Lyman alpha lines from the earliest galaxies. The neutral medium scatters them. An additional projector is the 21-centimeter line. It should map cold and hot spots relative to the microwave background, turning the dawn into a three-dimensional movie. While large installations are just beginning to create a reliable map, new generation telescopes are already detecting increasingly earlier galaxies, including candidates at Z greater than 10, hinting that the light ignited earlier and more efficiently than expected. And the chemical signatures, unusual element ratios in the ultra-metal poor stars of our galaxy, hold the memory of the first explosions, like soot on the walls of a workshop where the universe's first metals were first smelted. Ninth fact. The arrow of time is the hidden direction of creation, why the past smells of order and the future of disorder. In physics terms, the answer sounds through entropy. The early universe, judging by the smoothness of the microwave background, was astonishingly smooth, meaning with very low gravitational entropy. The curvature of the sky is almost flat, masses are distributed without large clumps, and this is an extremely uncharacteristic state if compared to what gravity loves. Usually, attraction leads to collapse and the formation of black holes, objects with colossal entropy according to the Bekenstein-Hawking formula. By rough estimates, it is precisely they who today give the lion's share to the cosmic disorder counter. A paradox arises. As the universe cools and expands, order did not disappear, but gave birth to structures. Gas gathered into stars, stars into galaxies, galaxies into clusters. This is the growth of gravitational entropy. In such a picture, the arrow of time is fixed by the condition at the start. The past is an unusually smooth state, from which it is easy to increase disorder. The future is increasingly lumpy. Inflation smooths out inhomogeneities, but itself requires a special initial field. Penrose formulates the Weil hypothesis. At the beginning, the free curvature tensor is almost zero, which sets the low entropy. There is also a philosophical trap. In an infinitely long heat death, random Boltzmann brains would be born more often than entire galaxies with history. But we see real past low entropy, not random delusion. This means the cosmos is arranged differently. If dark energy is a constant, the distant limit resembles de Sitter space, with its own horizon and entropy, where gradients for work become increasingly rare. And yet, the thread leads from the beginning. Creation is not just the equations of motion, but also the choice of an unusual, very ordered frame from which the film can start at all. The 10th fact. The phrase, "the universe arose from nothing," sounds striking, but in physics, every word requires clarification. Nothing in the philosophical sense is the absence of everything, including laws. Nothing in field theory is vacuum, saturated with quantum degrees of freedom and fluctuations. And before might simply be an incorrect question if time itself appears along with space. Competing scenarios for the beginning exist. Hartle-Hawking's no-boundary proposal, where early geometry smoothly rolls up time into a space-like one, thus avoiding a classical singularity. Vilenkin's tunneling, by which a tiny closed universe quantum mechanically slips from a state without classical space into an expanding world. Cyclic or ekpyrotic models, where the past is a contraction and a smoothed bounce. Loop cosmology, which replaces the singularity with a quantum bounce at Planck densities. All differ in details: the spectrum of initial perturbations, the level of gravitational waves, subtle anisotropies. In principle, this is observable, but not yet resolved. Popular also is the idea of zero energy balance. Positive energy of matter can be compensated by negative gravitational energy. And the global law of energy conservation in an expanding cosmos, in the strict sense, is not defined at all. There is no universal space-time clock. Hence the thesis: from nothing does not mean from absolute void, but within quantum gravity, an initial transition is possible where usual categories lose their meaning. Even bolder sound ideas of baby universes. A bubble of false vacuum under certain conditions could inflate into a separate world through a neck inaccessible to us, but these are speculations at the boundary of theory. To date, the honest conclusion is this: physics can describe the very early moments and offers several mathematically consistent beginning scenes, but the question why exactly like this remains open, separating the boundary between verifiable science and carefully marked metaphysics.